Hi, I'm Charlie Jackson. I'm chair of the IEEE Online Forum on Climate Change Technologies. We're having our fourth session today, and our next set of sessions will start in December. I want to thank our main sponsor, the IEEE Future Directions Committee, and I want to thank our patrons, the Circuits and Systems Society, the Electron Devices Society, GRSS, NPSS, and the IEEE Transportation Electrification Council, and regions 1, 4, 6, 8, 9, and 10 for being patrons. Here's the schedule at a glance, and I want to focus on what's coming up. Our talks start at 6 a.m. Pacific time, 2 p.m. England time, and 6:30 India time. And we'll start off December 2nd with a talk by Siegel and Chamberlain on cross-disciplinary collaboration. We'll have an interesting panel discussion by Karen McCabe, um, one panelist that attended COP. We'll have talks on December 3rd, 4th, and 5th, and that'll outline the program. So I hope you can all join us for the additional talks that are coming up. Thank you very much. And I'll pass the baton now to Mitradeep, and maybe Roberto, you'll pull up your files.
Okay, thank you, Charlie. Hello, everyone. Welcome to the 2024 IEEE Online Forum on Climate Change Technologies. Thank you all for participating in this event. For your information, copies of the presentation will not be shared. Instead, check back later the OFCCT website for the on-demand recordings for each session. Please submit your questions and comments via chat box. And with this, I would like to introduce our speaker today, Dr. Roberto La Rosa. Dr. Roberto La Rosa is an esteemed electrical engineer with a master's degree from the University of Palermo and a PhD from École Polytechnique Fédérale de Lausanne. Pardon my pronunciation. His doctoral thesis, which merited the prestigious Thomas Gessner Award in 2023, concentrated on pioneering strategies and techniques for the autonomous operation of wireless sensor nodes via energy harvesting and wireless power transfer. Since his tenure beginning in 1997 at ST Microelectronics, Dr. La Rosa has been instrumental in various capacities. His expertise has been integral in the design of high-frequency PLLs for clock generation and signal recovery, fiber optic transceiver systems, power management integrated circuits, and the development of analog, digital, and mixed signal bipolar and CMOS circuits. His proficiency in IC mixed signal design and ultra-low power applications has been pivotal in advancing these technological areas. Currently, as a research senior staff member at ST Microelectronics, Catania, Dr. La Rosa's research is focused on ultra-low power applications, wireless power transfer, energy harvesting, and high-frequency power conversion. He has authored several influential papers and holds multiple patents in these fields, underscoring his leadership in energy autonomy for wireless sensor networks. In addition to his research activities, Dr. La Rosa is an associate editor of IEEE Transactions on Agri-Food Electronics, where he lends his expertise to the advancement of electrical engineering, contributing significantly to the growth of this vital area of study. With this, I would request Dr. La Rosa to start his talk.
Okay, good morning or good evening, everybody. Thank you very much for this introduction, and I'm so glad to be glad to be here this afternoon to talk to you about strategies, techniques, and system for powering low maintenance and maintenance-free wire sensor node. So, So I work for ST Microelectronics, and I am an ultra-low power applications team manager. So I deal with ultra-low power. So ultra-low power to basically try to be powered through energy harvesting signals. So my presentation outline is, my presentation will go through describing the problem and the solution that we try to solve. We describe a system on chip for energy harvesting and wireless power transfer. And I will show some example on how to power a wireless sensor node for wireless power transfer, and also application examples about how to power a wireless sensor node for energy harvesting. And I will finish with conclusions and takeaways. Now, so let's go ahead. So what is the problem? The problem is that, so today we are talking about IoT with a very good perspective from the business point of view. I mean, we are expecting to grow and to have trillions of nodes by 2035. So we are going to increase massively the number of sensors. But is it sustainable the way we do today? So today, the wired sensors are either wired, and in this case, we don't talk about the wireless sensor node, or if they are wireless, they are battery powered in most of the cases. And of course, going to trillions of nodes installed, that means to be able to replace and dismiss 274 millions of batteries every day worldwide. And this is in the very best very best case, where the perspective is that a battery will stay alive for 10 years. I never seen so far a battery staying alive for 10 years. So 274 millions of battery means that the massive IoT as of today, with the techniques that we are using, is basically unsustainable. And we very likely, as it is, it will not fly. So we need to find a solution for that. That's the main problem. And what is the solution? Well, the solution we propose is that, of course, we have sensors that must be battery powered. Because it's not easy. They must be real time. We want an answer in a very short time, and in this case, we cannot get rid of batteries. And in this specific case, where sensors must be battery powered, we can try to extend the battery life as much as possible. And we will see that one of the key solution is to null standby power consumption. Another possibility that we can do is that we explore as a solution is that still in battery powered devices will basically try to make the maintenance as easy as possible. Because if we are going to put millions of nodes, that would be unsustainable, not only from an ecological point of view, because of course we have to dismiss all these batteries with, and these are of course an ecological battery. But it's also unsustainable from the maintenance point of view. I mean, if I have to put sensors in a school or in an hospital, I'm going to be I'm going to handle thousands of sensors, and after 3-4 years, I need to replace all these batteries, and of course, all this maintenance operation is a cost that we would like to avoid. So if the sensors must be battery powered, then in this case we propose to extend the battery life as much as possible. We see that we can double basically the battery life by nulling standby power consumption. And in this case, so the maintenance operation will be not every 3 years or every 6 years. Another operation we can do is to try to make it easier. So, and in this case, we will propose and we'll discuss how to do a wireless battery charger over the air, over the distance. The ultimate solution is when we don't need a real-time sensor. That could be, for instance, a temperature sensor or humidity sensor. I mean, sensors that are going to log variables that have a very long-term gradient. So temperature is not going to change any second. So if it allows us to harvest energy in a couple or in a short time, then in this case we can also discuss about getting rid of the battery. And this is very attractive because, of course, if we get rid of the batteries, we don't need to, we can, this is, of course, we don't need to replace batteries. The maintenance operation is null or very minimal. And also, we don't have the problem of ecological problem of dismissing the batteries and replacing the batteries and etc. So we will explore this scenario and with different solutions. Now, we start with a system on chip that we have designed specifically designed for energy harvesting and wireless power transfer. It's of course an ultra low power design. This is an integrated circuit that is this is the block diagram of the integrated circuit that has been specifically designed for energy harvesting and RF wireless power transfer. RF stands for radio frequency. As you can see here, we have the core of everything is the ultra low power management. And in this case, the ultra low power management has got the main specific performance is the quiescent current. In this case, it's been designed to have a quiescent current as low as 100 nanoampere. Why 100 nanoampere? Because we want to harvest energy in the order of microwatts. So if I have a current of 1 microampere, of course, the quiescent current must be at least 1 order of magnitude below to be negligible. In this case, our spec is 100 nanoampere. And with these microwatts, we can basically, in radio frequency, we can achieve a distance of the power transmitter as high as 8 meters. By, of course, respecting the most restricted regulation at Europe, it's restricts the power to transmit to alpha watt. In fact, in order to allow RF wireless power transfer, we have also integrated the RF to DC converter. And one of the specific performance of this RF to DC converter is the sensitivity power. And this design has got minus 22 dBm at 868 megahertz. And this sensitivity allows in free space to achieve a distance between transmitter and receiver of about 8 meters, provided that the transmitter can transmit up to half a watt, which is the maximum power that is possible to transmit in Europe. In the US is 4 watts, but we are relying on the real worst case. And also the RF to DC converter normally, unfortunately, is not a very efficient block. In fact, we have achieved 55%, which is one of the best in class in terms of percentage. Normally, this kind of system have an efficiency around 40%. There's a huge literature on that, but between 40 to 50%, and it's really hard to get over this number because, of course, we need to bypass the threshold voltage of the converter diodes. Now, this system, you see, we have a neutral low power management and a RF to DC converter. So we have integrated everything is possible to integrate in silicon. So we can get the RF power and convert into DC power, and then we will see in the application that we can do several different operations. So this is the picture of the layout of the IC design. And it's important that we have used 130 nanometers CMOS technology, and this is done to also to be compliant with low cost. So we are using a technology that is not a state-of-the-art technology. It's a good trade-off, and this is done on purpose because, of course, once we have to deploy a huge number of these sensors have also to be low cost. So these applications are also cost sensitive. So by design, we need to think ahead of that. Also is important that the area, so the chip size is just a prototype, it's not that big. So from the cost point of view, we have seen that it's manageable. As I told you before, at the core of everything is the ultra low power management, and the ultra low power management embeds a nano power voltage reference. The voltage reference is basically the most basic block that we need to have in the power management. And here we have designed a nano power voltage reference with a current consumption of 25 nanoampere, which is a quarter of our budget of 100 nanoampere. This is all done of CMOS and is a voltage reference that is as an output voltage of 0.8 volt and a very good temperature compensation. Another sensitive block, we need to put comparators. We need several comparators because we need to monitor the energy that we are investing. Our system is working between two voltages that a minimum voltage where we basically do not turn off any longer the system, and an high voltage. Between VH and VL is where we harvest the energy. So the energy we harvest in an energy storage, which is a capacitor, depends on VH and VL. In particular, in a capacitor is 1/2 the value of the capacitor, VH to the power 2 minus VL to the power 2. So we need to constantly monitor those voltages, and the comparator is important. Of course, while we are harvesting, which is where the voltage is going up, which is the energy harvesting phase, the power consumption must be very low, and this is the tricky part. In fact, we have a max static current consumption of the comparator, which is 4 nanoampere, that must be added to the nano power reference, which is 25. And we had also the configurable voltage threshold system, we little by little end up at 100 nanoampere, which is our maximum budget. Now, another sensitive block, as I told before, is the RF to DC converter. That is an inherently inefficient power converter, but it's the best we can achieve to do this job. And because it's inherently inefficient because these transistors have a threshold, and part of the power got lost in order to bypass the threshold of the transistor. On one side, we are trying to decrease the threshold voltage, but by doing that, we increase the leakage. And leakage is basically something where also the leakage of the transistor is a power that we lose. So there is a trade-off here between threshold voltage and leakage current. It depends on many things: the process, the voltage, etc., etc. So for this application, we have been able to get power sensitivity of -23 dBm, and in fact we can do a minimum output power of -26 dBm because there's an efficiency of 50%, so we get half of the power. So we go from -23 to -26. And the maximum DC voltage is 2.5 volt with a current of 1.5 microampere. So basically we have an actual power of 2.5 microwatts, which is what we get if we have a power transmitter 8 meters away in free space. So what we can do with an integrated circuit like that? So we can power wire sensor node through wire power transfer. And one of the applications we have been thinking at the beginning is to note standby power consumption by using wire power transfer. Now, standby power consumption is not only something related to the wire sensor node, but it's also something related to the appliances that we have in our houses. I mean, TVs, all kind of appliances that are remotely controlled. And there's a study that only Europe, basically the standby power consumption accounts for 43 terawatts hour. That means that is the equivalent energy produced by 4 nuclear power stations. So in other words, if we really have been able to solve this standby problem, because the standby, of course, the standby power consumption is something that we use to do nothing. So we are paying power for nothing, just to keep the system in sleep mode. Of course, this is an inefficiency. So if we can avoid the standby power consumption, we can save a lot of power. And this is quite evident in a wire sensor node. I mean, normally in a wire sensor node, even if the standby power is very, very low and relentlessly, the designers are trying to keep standby power consumption as low as possible. Still, since the number of hours where the system goes in standby is very high, the energy that is consumed in standby, which is the product of the power and the time, is still high and is comparable to the active. We keep a system in standby for 20 hours, 20 hours, let's say, and active for 4 hours. So, and there is an order of magnitude between standby and active. So at the end of 50, between the 50 to 70% of the energy that of a battery is lost in standby. So it's a consistent loss. So if I can renew standby power consumption, I inherently double the life, and I can basically double the time where I need to go and do the battery replacement or the maintenance. Of course, I reduce a lot the cost, because the cost of the maintenance is not really the battery, which is most of the time inexpensive, but it's the labor to do it. So how do we do that? So on the left, you see the state-of-the-art solution where we lose 50% of our energy budget. But on the right side, basically, we decided to put a switch in between the battery and the wire sensor. So now the switch, if the switch is open and no current will go to the wire sensor node, so the standby power consumption is gone because there is an open circuit here. The problem is, how do I activate this switch? Well, the solution we propose is to do remotely through RF wire power transfer, where the distance between the transmitter and the receiver can be up to 8 meters. So 8 meters away, like in a TV, we have 4 meters normally, but up to 8 meters, I can provide enough energy through the RF to DC converter that I can close the switch. And once I close the switch, I activate the wire sensor node. So I haven't even driven wake up in this case. So I don't need, I don't lose standby power consumption any longer. And when I want to activate the wire sensor node at that time, I have it. So the goal is achieved that I can extend the battery life. But as I said before, we can do the same also with appliances that we have in our house by saving up to 4 nuclear power stations. So how do we do that? Well, if I have alpha watt, that means my transmitter is between 7 to 8 meters away, and this is the carrier, and I send the power. I receive the power, and the power I can store this power that I receive, which is much lower than what I transmit, of course, in my storage capacitor. So I have some energy. And if I store the power into the capacitor, at the end I have the energy, and the energy depends on the voltage VH and VR. So at the moment I have enough energy on the storage capacitor, then I can decide, because I know by design that the storage capacitor that I put aside is big enough that when I reach VH, I can sustain the power consumption of the board chip. All at that point, I turn on the system. But at time zero, if you can notice, that there is no possible way that the battery supplies current to the wire sensor node, because the DC-DC converter has got an enable, and if the enable is 0, there's a very high impedance between VIN and VREG. So we have a very high impedance within here, so no current will flow here at all. So what we do is we harvest the energy. At that point, only when we have enough energy, and this is the job that is done by the ultra-low power management, only at that point, I basically have also the data. And if the data match what the address of my circuit, only at that point, I issue the enable, which is this red line, high. And when the enable is high, I turn on the DC-DC converter. At this point, basically the battery will provide energy to my wire sensor node that I can keep alive as much as I need. And once the wire sensor node has done its job, I can put the whole system is shut down. And so if because it's shut down, I'm again, the impedance here is going high again, and no current is flowing from the battery to wire sensor node. So I only consume the quantum of energy that I need when I need to do a sensor job through a wire sensor node. So, of course, all the standby is saved, which is 50% of the actual budget in the battery. Well, so of course, doing that, we save a lot of energy and we double the maintenance time. But even if we move this is just moving forward the problem. Instead of every 3 years, I have to replace the battery every 6 years. It's still maybe it's better. Maybe I'm not happy with that. So one thing we can do is instead of going there and replacing the battery, that most of the time we need to understand that these sensors are placed in places that are not easy to, are very hostile. I mean, sometimes the sensor could be behind the wall or on the top of the roof. I mean, are places that they need a complex maintenance operation. So something we could do is to use the wireless wireless power transfer to implement a wireless battery charger. So the idea is that if I have a power receiver, which is my wire sensor node here, if I can put a power bank or an equipment, a power transmitter on a table by covering a distance of 2 meters, and I leave here for enough time, then I can charge over the air my node. So this is from the power point of view, from energy point of view, is a disaster because that wireless power transfer is very inefficient. But from the total labor point of view, is a very convenient way to do it. So from the maintenance operation for the labor that I have to pay for the maintenance operation, of course, this is quite convenient instead. So, and to do this, what is important is basically to have a very good. Oh, sorry. It is we need to have efficient a very good efficiency, power conversion efficiency, and we see that leaving the power transmitter on the table after several hours, we recharge the battery at a distance of 2 meters. So this is a convenient way to do that. But still, we are in the field where we have sensors with battery. Now, there is a possibility that in some cases we can get rid of the batteries. And as I said before, this is when where the variable that we need to monitor. Let's have in mind the temperature doesn't change so in a very short time. So we can monitor in a steady state. And in this architecture, as you can see, the battery is gone. We don't have a battery. We have a storage capacitor, which is not huge. It's in this case is 2.5 nanofarads. And this is a system where basically we transmit power from 1.2 meter at 900 megahertz, and transmitted power is alpha watt. And we have a very heavy load here because we need to provide 10 milliampere for an active time of 50 milliseconds. But as you can see, what happens here is that we send the power, we charge the storage capacitor. What we see here, we store the red signal is the voltage on the capacitor. And every time we have enough energy, we just transmit sensing through a Bluetooth energy radio. And the transmission at these yellow spikes. So this is a quite interesting system because I don't have the battery. I can transmit and I have the sensing. There is a very specific case where we use that. And this is a very good example because with this system, we implemented a wire sensor node into an oven, which is a place where even if I wanted to put a battery, I cannot, because a battery into a 300 Celsius oven is not going to be it's not going to be safe. So what you see here is a system where, I mean, modern ovens can cook the food the way we want. I mean, we can program, for instance, to have this piece of salmon, which is crusty outside, very juicy inside, and we just have to set our requirement into the oven, and the oven magically will modulate the power to cook the food the way we specified. But the necessary condition to do that is that we need to know the temperature from the inside of the food. And this is why these ovens, they have this wired probe. But the wired probe is not really convenient because, I mean, they get dirty, they make it difficult to turn the food at the right moment. So a customer came to us and asked to do an application where this was wireless. So they wanted to implement a wireless probe. A wireless probe means, in this case, battery-free probe. So the way we implemented that is that we put a Bluetooth transmitter in the oven. So where we have a good power. So into the oven we have we can get the power from the main. While into the food, we had to put this nail, and into the nail we have the power receiver, the Bluetooth Low Energy radio, the storage capacitor, and the antenna. It's outside the bowl. Now the electronic part goes into the food where the temperature never gets higher than 100 degrees unless we don't burn it. Okay, so this is basically the implementation what we have seen before. So we send the power through the oven, we get the power, and constantly we monitor the temperature inside the food. You see here, you have 3 different temperature sensors to see the temperature into 3 different points inside the food. So this is a complex application because we have several problems, and one of the most problematic was the mechanic to get all the electronics into a diameter of 4 millimeters, because the output diameter must be no bigger than 5 millimeters, otherwise we lose the taste of our food. And the antenna went inside. But it's a very good example on application, even of an application which is entirely wireless. Another application, another example, applicative example where we use that technology is to monitor luggages. So today, the state-of-the-art technology is still the barcode. So when we go into the airport, they put the barcode to identify and track our luggage. Barcode is very well established, but it's not the best when our luggages get lost. Because if the luggages get lost, there's a need of an operator that must go to scan one by one all these barcodes of the luggages until they find the luggage. So one way that be required to do it is very automated. So the idea is to put a tag in the luggage, one or more tags in the luggage, which that they must be passive, because of course nobody wants the batteries for 2 reasons. One, first is because the minute I need my luggage, maybe the battery is out of charge, and second, because into the airplane is not safe or required to have batteries. So what is the idea here is that we have the tag in the luggages, and also we put hotspot along the conveyor belt. So these are big red dots are the hotspot along the conveyor belt. So while the luggage passes through, emits the hotspots and get charged until we get enough energy that we can send a Bluetooth energy beacon that goes in the cloud, and magically I get a message in my cell phone that my luggage is in the airport or is being lost somewhere. So this is another technology where we get rid of batteries and we use wireless power transfer in a quite good distance. And to do this, we need to work on performances, so power conversion efficiency and also sensitivity of the IC. Now, so that's all basically about the wireless power transfer. These are just a couple of samples. Another way to get rid of batteries is to use energy harvesting. I normally do a distinction between wireless power transfer and energy harvesting, because wireless power transfer requires to have a power transmitter. So if, as of today, for the kind of performance we have in wireless power transfer, so with RF energy harvesting, let's say, it is required to have a power transmitter. It's not possible to harvest the environmental energy that we have about RF. because all RF transmitters are they have to comply with the regulation that is done to prevent RF. On the other side, the sensitivity of the system is limited to minus 20, 23 dBm. And the noise we have for the regulations that the power is minus 40 dB. And so today with current technologies, we are not able to catch minus 40 dB of power, minus 40 dBm of power. So today, the only thing we can do is to put the transmitter at a certain specified distance from the receiver and just send the power. So this is more a wise power transfer than energy harvesting. Energy harvesting instead is intended something like I leave an object on the table, there is light. I don't have to put a light transmitter, and I just harvest energy, and magically my system works. So again, how to lower maintenance costs? Well, the problem is still wire sensor node maintenance, and the solution is, in this case, energy harvesting and ultra low power design. The two things go together. So if we want to use energy harvesting, we need to be able to relentlessly lower the power of our design. So it must be ultra low power. So now we need to go to nano power circuit architecture. What are the requirements of a wire sensor node? Of course, we don't want the wires, but maintenance is important and low cost is important. So this, I would say, is are the most the biggest problem that engineers are facing. How to null maintenance, so getting rid of batteries, and at the same time with low cost solution. And on top of that, of course, we need to have a compact form factor. I don't want to use a photovoltaic panel which is as big as a paper. And in this another aspect we need to face when we are going to massive IoT, so a huge number of sensors, is the end of life. Of course, this system, we need to think about system that at the end of life we can dismiss easily, are recyclable, are sustainable. And so if we don't want to know wire connection, so energy autonomous battery free, we need to make them energy autonomous battery free. Wireless communication, it must be easy to configure. In other words, we need, the feature is that they must be set and forget device, because we have trillions of this node, but also they have to be sustainable. In fact, one of the things we are doing, we are trying to work with with materials like cork. I don't know if you can see this, that are basically sustainable. So they are not carbon based, and they are good enough as a package. So the idea is not only to get rid of batteries, but in an holistic way, also to try to build the system in a way that at the end of life is also low cost and also sustainable. And this requires the use of specific materials that at the end of life simplify this mission of these items that are going to be in the trillion order. So the first product this is a prototype. The first product we engineered is an energy autonomous battery-free device that uses Bluetooth to energy connectivity. Now, the Bluetooth to energy connectivity is the connectivity that has the lowest power, the lowest energy requirement. In fact, Bluetooth is low energy, and this is the best in terms of performance for low power, but it's not the best in terms of range. I mean, the range we can expect with Bluetooth to energy is 20, maximum is 20 meters around. So it's good for low power, but in terms of communication range, is in some application is not ideal. It's ideal, for instance, for wireless personal networks. So in application related to objects that we wear on our body, this is a very good. Or if where the communication range is not expected to be high, like in apartments or stuff like that. So this is a very good example where we used here a very very small form factor. The system is big at only 2 centimeter by 2 centimeter. And this is just a prototype, so we can make it even smaller. The storage capacitor is implemented with these two small capacitors. So it's just 220 is just 400 microfarads. So it's very small and cheap SMT capacitor. And all this is built with off-the-shelf device, which is to me a very important point. And that means that these applications now are not research anymore. If we can build with off-the-shelf devices, now it's something that we can we can go to a very high technology ready level. So we don't need to wait for the next possible ASICs, and also the costs are low because off-the-shelf devices normally are not very expensive. So we are using that with technology. We are doing this. We are implementing energy harvesting and Bluetooth to energy tag with something that we have in our portfolio. So everything is done with off-the-shelf device. In fact, we have an amorphous silicon solar cell by Panasonic, which is commercially available. We have an STM32 low power line from ST Electronics. In this case, we have a humidity temperature sensor and also the Bluetooth energy radio module. But this system not only senses humidity temperature, of course we could add the other sensor, but incidentally is a very good monitor for light, because we use simultaneously the photovoltaic cell to for energy harvesting and for light sensing. And this is something which is built in with the system. So the idea is that we know cycle by cycle the energy that we have available. So the energy is fixed by design because it depends on the storage capacitor that we design once forever, and also from the voltage threshold VH and VR. So the advertising time is something that I can measure also at the base station, where I have unlimited power inherently. It's basically a way to measure the power of the light, which is the luminosity. So because the harvested energy is constant, every cycle is constant. So the harvested energy is basically the product is equal to the product of the input light, which is the power, times the advertising time. So if I can measure the advertising time, which is a very simple measurement I can do, I just need the timer at the base station, I can basically indirectly measure the light power. And in this case, I've done a luxometer, which is very inexpensive, because I use a simple photovoltaic transducer to do two different functions. So this is, of course, the system, as we will see, is agnostic also, but this is a characterization of the light sensor. In this case, it starts from 400 lux, and we see that the time between two consecutive beacons is a function of the luminosity. So if I increase the luminosity, the time between two different beacons is lower, lower, lower. So the system gets faster because I'm providing more power. So we harvest the energy in a lower time, and we have beacons that are closer to each other. Of course, Bluetooth Low Energy, it's ideal because we have the Bluetooth Low Energy receiver in every portable device, in every tablet or in every mobile phone. So it's really easy to read the data, because we just have to write to engineer an app, and from the app we can have the monitoring of the light intensity, the temperature, humidity, something very, very, very inexpensive, because an app is very low cost to implement. Our system, I started talking about light intensity, and photovoltaic cell, but the system is virtually agnostic from the energy, from the power point of view. So I can use a photovoltaic cell, or I can also use a piezoelectric harvester that basically it is a transducer of the vibrations into electricity. So instead of having a photovoltaic cell, I can use a cantilever like this, and by vibrating produces electrical energy for me. And in this case, instead of measuring the light, I'm measuring the acceleration. And so I can still use the piezoelectric harvester to indirectly measure the acceleration. So not only still I keep the dual use of the harvester, and this is true for everything. It could be for a thermoelectric generator. This is true for all the harvesters. Now, here we use this system to monitor the temperature and the humidity internally and externally of an hive. So what you see here is an hive. This is basically an hive, a Maya hive. So all these bees are stingless, and they stay into this hive that is called the ovum. It's basically a wooden pipe where they do the bee leaves, and we have put these transistors, we have put these circuits, internal and external, to measure the temperature outside the hive and internal to the hive. But the peculiarity of this system is that as an energy harvester, they are using not the light or the vibration, they are using the power that is generated by these plants. Yes, because the plants can be used as a plant microbial fuel cell. So the soil of the plant can generate energy. And it's basically, a plant is a kind of solar cell, because the light is creating the photosynthesis, and the photosynthesis is creating the glucose or through the roots, and all this is releasing charges in the soil, and we can use these charges to we can harvest these charges to have energy. And once we have the energy, we can run. It's interesting that with all these plants, they can power our system, and we are battery free, and everything is nature based. Of course, this is a system that does not have a very high technology ready level, but it's a good prototype, and it gives a good idea of what can be done by developing this technology, especially in the agri-tech industry. Of course, by following this, even something we can do with this system is to create a revolution in the irrigation system. I mean, in our climate change, also we have a problem of water, and that year by year I see that is increasing. Now, as of today, the irrigation system is based on empirical practices. So we give some water, and maybe it's enough for the plant. What we can do is instead to establish a communication between the plant, and this can be done now because the battery-free devices allow to be disseminated. So I can put as many sensors as I want. I mean, I don't have to take care of the batteries now. So I can think large scale. I can put sensors, and these sensors can give me an idea of the water needs of the plant, or in this case of this grass field, and communicate with the water controller. But interestingly, in this case, we provide the water on demand when the plant is asking to have the plant. So we want to bring the plant to be self-sufficient and send a message or ask for the water or nutrients. But what is interesting here is also the water controller can be battery-free, and is actually battery-free. And we have engineered this system here because this is the water control system. This is our electronic, and here we have the electro valve. So at time zero, we see with this electro valve, the plant is asking for water. We are providing the water, this light. But there's a super cup here, and there's not a battery, that every time this system is going to switch on and off, the energy is going lower and lower. But we monitor constantly the energy, and when the energy goes red, goes low, we can turn on this branch here where we have a turbine. So the turbine is our harvester, and we re-harvest the super cup, and so the system is constantly is powered by the water. So this water control system is highly simplified with respect to what we have in the state of the art, because in the state of the art we have a system where we need to provide the battery, or we need to provide some wiring to provide the energy up to the main. Here is that the only thing also in the installation we need is just to screw the pipes. That's all. And the energy will be provided by the water. The water flow has got some energy, and we use that by using a simple turbine. And out of these ideas, now again, this is not, it's going beyond research. So we have a commercial available product. Claver, which is a very well-known brand in Italy for gardening equipments, has engineered this concept, and now we have the very first water control system, which is battery-free. So it's entirely powered by using the solar power. So, and this is a system where we have electrovalves and just a photovoltaic cell. And this system does not need any battery. Is a very good product, and this year has been very successful. So the good thing is that we now have commercial available products. So we have products on the shelf out of these ideas. Now, from here, of course, we are going to explore something by using only one device. So our architecture is used on our chipset, and the only thing we need is one chipset, which is a microcontroller that is also embedding a radio unit. In this case, for instance, if we use BLE connectivity, the system is integrating a radio unit with a BLE connectivity. And as you see, the chipset is basically taking care of the energy management, is built in the microcontroller. Then we have the microcontrol unit in the traditional, intended in the traditional way. So the interface with the sensors, etc. And then we have the radio unit, everything embedded in one single integrated circuit. This is important because all this brings us to have a low-cost solution. The lower is the number of components that we need to put in an application, the lower is the cost. And all we need to add is the energy transducer, that it depends on the use case. So we've seen before that maybe I can use a photovoltaic cell or a plant microbuffer cell, or maybe a vibrational or a cantilever. What we need to put aside is the energy storage and the energy backup. So what are the energy storage and energy backup? Commonly, these are energy storage is a capacitor. Energy backup could be either a supercap or a solid-state battery. The solid-state battery is a good trade, is a good compromise between a traditional battery and a capacitor, a supercapacitor, because a solid-state battery can survive up to
Sorry to
20 years.
Roberto,
Oh.
we have 10 minutes left, and then we will take a few questions also.
Okay. Yes, I mean, I'm going through the examples now, so I can stop whenever is needed. Okay, so the same, so out of this, we have basically one of a startup, of which I am a founder, is basically implementing all these applications in several different sectors. Could be agri-tech, home and office automation. Here you see here, this is a good requirement. So in Italy, we have a lot of museum, and if you go into a museum, you have a lot of arts that needs to be monitored. Now, monitoring arts into museum is a huge number of arts. So up to now, up to today, is not done just because we don't have the technology to do it. Because putting batteries in every piece of art, in every picture, is kind of crazy. So with this technology, we're going instead to monitor any single piece of art in terms of temperature, humidity, presence of people, and so forth. Now, Bluetooth Low Energy so far is good, as I said, for short distances. We have done some tests, and we have seen the maximum distance in agri-tech in wires is 160 meters, which is not ideal in agri-tech. That's why we also propose LoRa connectivity. So we did a job to understand if this the LoRa long-range connectivity that is up to 15 kilometers, that can cover up to 15 kilometers, is compliant with energy harvesting? And the answer is yes. Long-range connectivity and energy harvesting can work together very well. And again, we have a single IC where we have energy management, microcontroller interface, and then you want to long-range connectivity embedded, so a single IC. And here you see this is an engineered version of the system. So we have the module here with the LoRa connectivity system, and the sensor in this case is a chemical sensor, the photovoltaic cell, and the antenna. That's all. What you see here, this gray box is here basically a supercup. With this, we have implemented an ammonia sensor, which is very important for livestock farming, manure management. There are many applications, especially in agritech and farming. Or also oxygen sensors that are these are basically battery-free oxygen sensors that are very important when we want to monitor the soil health or even the fruits.
Because we have a few questions, can I take one question from the chat? Because we are running 5 minutes, then probably this is engaging.
Yeah, sure. Please. I prefer. I mean, I can keep going with the samples, but I prefer the questions, of course, definitely.
So the first question is from Sagar. He is asking, can you tell me about how can we apply nulling standby techniques to battery-powered appliances to extend their battery life and reduce energy consumption?
We need to go backwards then. Well, the idea is that if you put an AC like that, you have a battery, and you put an AC where you have an RF to DC converter, and you put the antenna. If you have if you have a remote control or something in your room, and the distance is about 7 meters, that you can put the system not in standby. You can start the system to go shut down. So you shut down your system, and when you want to activate in a regular way, then you can send some power just to activate this system the way I show you. So you basically put transmit some power, you receive the power, harvest the energy, and when you have enough energy, then you basically enable the DC-DC converter. You have the battery that is providing energy to the wire sensor node. So in this case, you just have to have a power transmitter for multiple sensors. Imagine you're in a room and you want multiple sensors, and all these sensors are basically without any with the battery, but they do not consume power when they are standby, which is a long time. Did I answer your question?
Yeah, I hope so. He also is interested to know the technical and economic feasibility of this technique, of this implementation.
Well, it's very economical because there is nothing more than I mean, there is just an integrated circuit. The integrated circuit normally is not very expensive, as I said before. We also designed the circuit to be low cost, and of course you need an antenna, and that's it. In some cases, for instance, in appliances, actually you have it reduces the cost. Because in an appliance, you need auxiliary power converter that just to keep the system in standby. So if you know the standby power consumption, you can get rid of the auxiliary power converter, which is way more expensive than this solution. So in a specific case, I can also guarantee a saving in the BOM. In this particular case, it's quite economical feasible because you just have to put an AC and matching network and antenna, something which is not very expensive in an application.
Okay, I see. So there is another question from Andre. He is asking, besides the positive impacts of less material usage, more specifically batteries, what could be other examples of positive impacts of the zero standby solutions?
Oh, well, a zero standby solution worldwide, as I said before, we save nuclear power station, or we can use that power to do something which is better. Okay, So this is a real saving because it's not working on a single TV. I mean, we have trillions of TVs or appliances worldwide. So again, in an economy of huge numbers, like our appliances in our houses, of course, you have a big saving. Secondly, as I said before, in the appliances, you can also save the auxiliary power supply, which is only there to keep the system standby, by using this solution. So
Okay.
you have a time zero you save in the BOM, and also which is something that you if you produce a TV you can touch, and then in perspective, of course, you can give a good end in sustainability.
Okay. Oh, I see. So because we have we are running out of time, so I need to close this session, and I would like to
Okay.
thank you, Roberto, for this very interesting talk. However, the audience may get in touch with you over email or some other means to get clarification.
Yeah, anytime. Thank you very much for your attention, and I hope you enjoyed this. Have a
Thank
good
you,
day. Bye bye.
Roberto. We already have our next speaker. And
No,
then
I'll be here. I'm just saying bye bye because I'm leaving. Okay.
okay, yeah, I see. Thank you very much, Roberto.
Thank you very much.
Thank you.